First, let's examine the joints that we have on this assembly. So at the front of this crankshaft, I have a spherical joint where this bearing is fixed in space. It's grounded in the engine block, it can't move, and then there's another bearing back here that is grounded in space. And so if I go to the properties of the spherical joint, so I have 3 degrees of freedom on that point. And the one that we're interested in then is the revolution around the axis of the crankshaft. This next joint then is I have a point line, and so the point line has 4 degrees of freedom. The point has 3 revolution degrees of freedom around the axis, but the one we're interested in is the revolution around the axis of the crankshaft, and then the translation along the crankshaft. But because we have the spherical joint up here at this end, the crankshaft can only rotate, it can't translate, but we don't have it. We leave that degree of freedom though free so that it's not an over constrained condition. Then we have a revolution joint between the connecting rod and the bearing. So the revolution joint is 1 degree of freedom. It can only revolve, it can't translate or move in a straight line. Then the piston is constrained such that it only has a 1 degree of freedom translational. It can only move straight up and down. And then the other end of the connecting rod, because it only has 1 degree of freedom, no translation down here, revolution, we don't want to over constrain it up here, so we have a point line. So it could theoretically translate, but because of the joint down here, it can't translate. And then it can revolve though around the axis of the piston pin. Had to be careful though to not over constrain the or have redundant joints on our assembly. And then I'll place a force on this piston, and I'm going to put it pointing down against the piston, and let's say 1,000 newtons. And then I'm going to monitor the velocity of that piston. So I'm going to go to the output grapher, and I'll go to that prismatic joint, and I'm going to monitor then the velocity of that piston, and we will go ahead and play the simulation. So as the force pushes down on the piston, it revolves around, and I'm doing 1,000 calculations here, and that's why it's slow. And then it will start to go back up, but remember the force is still pushing down on that piston, and so it'll only go a certain distance, and then it's going to start going back down again. And let's do fewer calculations, maybe we'll be able to see that better. It will start oscillating back and forth, and so let's do 100 calculations and we'll see that. Okay, so it goes down, it starts to go back up, and we need to run a little bit longer on a time. So I'm going to go 0.1 second. Okay, so it'll start going down, and it'll start going back up, but then it'll go back down because the force is pushing it back down, and it'll just oscillate back and forth. I'm going to put this back to 0.04. Alright, so we don't want this force pushing down continuously. As this piston gets down to bottom dead center, we want that force to cut off. So I'm going to edit the force, and instead of having a magnitude of 1,000 newtons continuously, I'm going to go to the input grapher, and I'm going to create some conditions or add some conditions. And so let's say we want a thousand, or 1,000 newtons of force, but we want that under the condition of if the velocity of the piston, and remember that was the prismatic joint, if the velocity of the piston, and all we had to do is select that variable name, is less than or equal to, when it's going down, the velocity is a negative value. So if it's a negative value, or it's less than or equal to 0, then we want the force to be on. And then when it starts going up, the velocity is in a positive direction relative to our assembly, and so then we want the force to cut off. And so let's see, we've got that set. I also want to display, have that force displayed, a vector. And let's try a scale factor of 0.0005. We might have to adjust that. Okay, so I've set the force to be on when the piston velocity is going down, which in this coordinate system is negative velocity, and then to turn off the force when the piston starts going up, which is positive. And so I'm going to display the velocity of the piston, which is the prismatic joint, and I'm going to display the force on or off as the piston moves. So we'll go ahead and start the simulation, and I see the vector for the force is on, now it's off, now it's back on, off, and it's going to gradually speed up and just keep going faster and faster and faster, because we don't have any limiting condition on the RPMs for the piston. So that's the next thing we need to do, or for the crankshaft, we need to limit the number of RPMs for the crankshaft. So let's rewind this, and we'll go back to construction, and I'm going to edit the force again. So again, here's the velocity, negative and then positive. When it's going positive, the force is off. When it starts going positive, the force turns off. When the velocity goes negative, or the piston's going down, the force turns back on. And so it just turns on and off as the piston goes up or down. I'm going to change that though, so I'm going to edit this force, and we'll go to the input grapher, and I want to put another condition in here. So I'll say, so right now I have, if the prismatic joint, if the velocity is less than 0, then the force is on. I want to add another condition, so I'll select add a condition, and I'm going to say and so I can check and or, so I'll say and if the variable spherical joint, the velocity v1 is the revolution around the axis, and if that is less than or equal to let's say 7,000 RPMs. Oops, 7,000. So that force will be on as long as the velocity of the crankshaft is less than 7,000 RPMs, and then it will cut off the force. So I'll say OK to that. We'll say OK, and go back to, and we'll clear this graph. We'll run it again, and so again the force goes on and off. It speeds up, but at some point the crankshaft reaches 7,000 RPMs, and notice the blue line, the force turns off. And so we've reached maximum RPMs. Now we haven't put friction on here. There's a lot of other things going on, but we were easily able to set those conditions for when the force was on or off. For the next step, I go through and for each of the joints I put in a dampening and a friction value, and then I'm going to play this again, but we know that it's going to reach the 7,000 RPMs. For the next test, I've applied various dampening values and friction values to the various joints, and I'm going to take the force off, so I'm going to suppress that, and instead I'm just going to tell it to turn a certain number of RPMs. So I'm going to go to the spherical joint, and I'll go to the properties of the spherical joint, and I will then that revolution around the axis, I will impose a motion, and I'm going to do a velocity of constant value 7,000 RPMs. Okay, so I'm just going to set it to run 7,000 RPMs. And then I'm going to uncheck the velocity of the prismatic. We know that the crankshaft will be turning a certain number of RPMs, but I want to look at the driving force on the spherical joint and the force on the point line at the other end of the connecting rod. So we'll go ahead and play this again. And I'll just go ahead and stop it. So there are a lot of other graphs that we can look here of various events that are happening. I want to look at I want to do an FEA analysis on the connecting rod at a particular, or at one of these maximum or minimum locations. So I'm going to right click here, and I'm going to search max, and I'm going to put a check mark here at that time step, and then I'm going to search for a minimum, and so I'll do a search min, and here's a minimum. Now actually let's do a search min on this one, and so here's a minimum on this imposed motion, and I'll put a check mark on that. So a couple locations where I want to, or time steps where I want to do a FEA analysis. And so I'm going to then export this crankshaft to the FEA analysis, and Inventor wants me to indicate where those forces are being applied. The one force, actually the revolution joint that was on the crankshaft, that force is being applied there, and then the point line is up here on the other end of the connecting rod, and I'll say OK to that. Alright, I'll finish dynamic simulation, and I will go into the stress analysis environment, and I'll tell it to create a study, and we're going to do a motion loads analysis. So I'll check mark motion loads, and I have two time steps that I check mark that I wanted to check at. So we'll do one of those time steps, and so OK. And so it brings in the various forces on the connecting rod at that particular time step, and then I can go ahead and run my simulation for the FEA analysis.